Was it too distracting? Do you want the hallway? Alright. Good. Logarithmic functions. You have to face a little bit of school. What are you doing? Really? Is it hard? Sounds like that. They just chill, right? Looking inside the ladder. Question. Section 3.2. Logarithms. What's the relationship that we saw algebraically? Why am I saying algebraically? Algebraically deals with what? How do we see math if it's algebraic? Numbers, letters, not tables though. That'd be numerically. Formulas, equations. Good. Nice. Good. Yesterday in the formulas, what did we see was the relationship between logarithmic functions and exponential functions? What happens if the exponential and the logarithm have the exact same base and they're together, like a log of an exponential or an exponential to the power of a log? What happens?
Cut it.
Cut it. Why? Because they are. What's the relationship?
Oh.
There was a name to a property yesterday that you wrote down. If you take log base a of a to the u, or a to the x, or a to the log base a of x, what was the name?
Inverse property.
Inverse property. There's the one-to-one, which said if the bases match for logs, the arguments match. But the inverse property, wait, why inverse? What do inverses always do to each other? Cancel. Break each other down. Like a square root and a square, what happens? Cubed root and a cube, what happens? Right? Plus and a minus, what happens? Right? Exactly. So what happens when you have an exponential to a log? As long as their bases
Are the same.
match or the same. And what happens if you take a log to an exponential as long as their bases are the same? Exactly. So, wait, what's the relationship between an exponential graph then and a logarithmic graph? If they're inverses, back to chapter 1, chapter 2, I don't know something. Question. What should their graphs do?
Reflect across
Across?
x-axis. Cross.
The y equals x line. Close. Reflect, yes, but reflect across the y equals x line. So remind me, what does an exponential function look like from section 1 of chapter 3?
Like.
Right? It's the fastest type of growth. He starts kind of slow and then he goes super fast. So if an exponential function looks like this, and if he goes through, bless you, do you remember what his intercept was? It's a special one. Just a general exponential function, y equals a to the x. Wait, it shouldn't be hard because look. On the y-axis, what is x value?
0.
So plug in 0. Anything to the 0 power is 1, as long as it's not 0, but a is not allowed to be 0, so we're good. So 0, 1. So what point is the logarithmic graph? Y equals log base a of x. What point is he going to have?
Oh, 0, -1.
Not
No,
negative
-1 and 0.
No, not negative 1. What happens? Inverse.
1 and
What
0.
happens to points?
1 and 0.
Positive 1, 0.
They're inverse.
Yeah, so the points switch, right? Can you guys see what the graph's going to look like for the log if it flips across the y equals x and if it has the point 1, 0 instead of 0, 1? What's it going to do? Yeah, it's going to swoop, right? Swoop, there it is. Okay, so there we go. Question, what kind of asymptote, I just said it almost, what kind of asymptote does an exponential have?
Slight asymptotes.
Oh.
Whoa, come on. Look, y equals x.
That's the axis of symmetry though, right? That's where it's symmetric, but this guy just goes. He's not getting closer to him. Who is he getting closer to?
Don't you have to consider both together?
Just the exponential. So then if he has a horizontal asymptote at y equals 0, what is the logarithmic one going to have? At? See, everything just flips. Everything just flips. If the exponential has a point of 0, 1, the logarithmic has a point of 1, 0. The exponential has a y equals 0 horizontal asymptote. The logarithmic one's going to have a vertical asymptote of x equals 0. So let's talk about the exponential one, okay? And if I were you, because if your notes are all in one color, it's going to be kind of hard to know which one's which, I would make him really bold. For me, it's blue, and blue's going to match all the rest of the colors on this page. But for you guys, you need to make sure that you know this is the logarithmic one, okay? We wrote both so that you can see the relationship between the two. But you gotta know. We've already talked about him. He's exponential. This one is the one we're zeroing in on right now. So what's the logarithmic function's domain? Uh-oh. Domain. Back in chapter 1, I said domain problems. Don't worry, we haven't looked at logs yet. Why do logarithms? Why does this logarithm have a domain problem? How left does it go?
Almost 0.
Almost 0. It's bounded by 0, but not including, not hitting 0. So how would I write that for domain?
Open parentheses.
Open parentheses at 0. And how right does it go?
Oh,
Infinity. Good. How left does it go? Only to 0. Exponential functions had no domain problems. It goes forever left, forever right. But logarithmic, because of that vertical asymptote, he's stuck. He has a domain problem. Range, how low does he go? Infinitely low. I like it. We'll say negative infinity. How high does he go? Positive infinity. Now, does he go as fast as the exponential one does? No, but he's still going up. He's still going up. X-intercept. He's an important point. 1, 0, right? You flip the y-intercept of the exponential function. Strictly monotonic. What's that mean? He's only doing one thing. What's the one thing he's doing? As you read him left to right, where's he going? Up. So he's, his snazzy term increasing everywhere on his domain. We already stated the vertical asymptote. Where is he at? X equals 0. And the logarithm is continuous. He's fine. He's connected with one smooth curve everywhere in his domain. No holes, no vertical asymptotes. Inside of him. There's one on the outside of him, but none inside. He's continuous everywhere on his domain. Now, we have a little dilemma to talk about. So let me quickly look at the next page and see if I want to talk about the dilemma yet. Oh, we already did all that. Okay. You guys were awesome. Let's go back. Let's talk about transformed logarithms first, and then let me go ahead and quickly summarize the domain problem with a logarithm that we're going to have to add to our other domain problems in our handy-dandy, hey, how do we find domains of functions, and when are they not just all real numbers? But first, let's just say, let's take this basic log and let's start changing stuff. Let's start changing stuff. Like exponentials, let's look or think about a shift horizontally. Let's think about a shift vertically. Let's think about dilations, kind of. Let's think about dilations, kind of. Let's think about reflections. And then let's see if we can actually, get the general idea for a few logarithmic transformed functions. But remember, just like with all the ones we did before, the parent functions with absolute value, with x squared, with x cubed, with, what else did we do? We didn't do sine or cosine. Square root, we did the square root of x. The easiest way to transform functions is to start with the parent function, take a few points, a few important pieces, and then move them, shift them, reflect them, and then connect. As you guys are writing, there's a plus b on the outside. Come on. What's that mean?
No, vertical.
If it's outside, which one is it? Oh, no,
Vertical.
Vertical. Because remember, we could say that this used to be the y value. This was the old y value, so the y's are adding b. which is why everything on the outside we say affects the vertical, or vertically affects the graph. So we're going to say B is a vertical shift, right? Because it's plus. A is just the base. And then C, since we're subtracting on the inside, what's that going to be? Horizontal. It's on the inside. Horizontal shift. How could a logarithm be reflected across the x-axis? Quick reminder if you need the visual. Across the x is this kind of flip. Would that be an up-down flip or a right-left flip? Right? Because what's up goes down, what's down comes up. So where would the negative need to go for the parent function? So you have to have a negative log base a of x minus c. The logarithm would need to be subtracted, or would need to have a negative. If we're going across the y-axis, that's a horizontal reflection, right? What's right is left, what's left is right. Uh-oh. Where would that occur? You need to have a negative on the inside. Yeah, next to the x. Now, there's a few different ways of writing it. One might be a little less confusing than the other. Basically, if you see a negative right by that x value, right in front of that x value, there is going to be a reflection. But you could either see it right in here inside negative x minus c, or you could also see it, which technically would still be inside. You could see it outside. But here's my question. Are those the exact same graph? If I were factoring out a negative, yes. So if I do see this, and if I'm trying to factor out, in order to be the same, this would need to be a plus c instead. Now, just before we go to the next page with transformations, let's just do a quick little exploration. I want you guys to get your graphing calculators out. Let's do a quick little exploration, because technically we could have done this all along with transformations. It's trying to ask the question, if you have a negative right by the variable, or if you have a negative outside the whole thing, what's the difference? Let's go ahead and take a quick sample problem. Let's see if I can get back in my notes. There they are. Okay, so along these lines, let's go ahead and do a quick discovery. The goal of what we're about to do is to describe the transformations occurring. That is spell occurring. Is it one? Yeah, it is, right? Oh, I thought it was two. That looks even worse. Okay. You know those words that just never look right? Yeah. Does that ever happen? And then they look right like every other time. It's just fun.
Yes, it's like
I think she's
occur. Occur. Type it into your phone and see what it autocorrect. There's no autocorrect.
You're welcome. Who looked it up?
Yeah, but then it's an extra R. Occur.
Oh, it's one R, okay. See, I was right when I thought I was wrong, and then you guys thought I was right, and then it just got wrong. Okay, so y equals.
That's why you listen to your gut.
It's a struggle.
The struggle is
For Tuesday. It is real, right? We were encouraged by it yesterday. Y equals. Struggle is real, but it's for a good cause. Y equals let's go ahead and do, ready? I'm gonna make it crazy. 2 minus log, let's just do common log. That way we don't have to do any of that nasty log-based stuff. And like Sean wouldn't be left out because he's not doing it and stuff. Log base 10, so let's make it common log of negative x plus 3. Graph them. And your goal is to take the graph and see if you can verbally describe all the transformations. The order might be important. And if some of you are like, but mine doesn't let me put a negative outside the parenthesis for log, what would you do? Double up. If you're like, but it doesn't let me put a negative outside the parenthesis, that's okay. Just put it inside.
Can we distribute it?
Technically you could. Technically you could, right? If I make it look a little prettier. It's up to you. 2 minus common log of negative x plus 3. Before we graph it, let's just talk real quickly. Some of you already graphed it, that's okay. Question, how many reflections should there be? 2. Why? There's a negative outside the log and there's a negative outside the x. What else is there going to be? 2 reflections and then 2 shifts. 1 horizontal and 1 vertical. Some of you would look at this and say, psh, it's moving to the left. Some of you would look at this and say, no, it's not. It's moving to the right. Huh. Some of you would say, it's moving up. And some of you would say, pull out the negative, it's moving down. Well, Steve, you can't be doing all those things. So what did you guys see when you went to graph, which kind of has us dealing with the order of transformations? I went past it. I have no idea what my Zoom is. Do you guys do Zoom standard? Nice. Is it just me or did my calculator freeze?
No, yeah.
Struggle, what's going on?
Miss Steve, what's going on?
What is going on? It wasn't too crazy, was it? Did anybody distribute? Did that help?
Yeah, we did, but it's still the same thing.
Ah, still the same thing. So that means that they're the same either way. What if we do this cool Zoom that I like called Zoom Box? Let me say, we need to figure out what on earth is going on right here. So I'm going to go ahead and start my box. You guys know Zoom Box, right?
Nope.
Ah, look! It's like clicking and dragging.
That's pretty cool.
How do you not know Zoom Box? That's sad.
Eric.
Oh!
Yo.
Hey, wait!
That's
It's going up higher! If it's going up higher, what do you think this is? Even though it's weird and it cut off because the poor calculator only has so many pixels, so it can only get so close. Oh.
Vertical asymptote.
Vertical asymptote. See, it's trying to get closer and closer and closer. And if we're not exactly sure what's getting closer and closer too, that's a little imprecise. Couldn't we trace it and say, hey, what x does it seem to get closer to? Right? Because a vertical asymptote is an x value. So look at the x. I have -5, I have -4, I have -3.
-3.
Sure looks like a -3 to me, right? Because -2.9, all of a sudden it doesn't exist. Which means -3 must be what it's getting closer to. So hold on. What happened?
The 3 right there, it becomes a -3 because horizontal. I don't get why it becomes an asymptote.
The normal logarithm does this, right? That's the parent function. Okay. How did it flip?
Negative log.
Horizontally, right? And how else? Vertically. Well, that kind of makes sense. So it flipped horizontally, like this. And then it flipped vertically, which would be like this. And that's kind of what it's looking like right now, right? But it's not down there.
Went up to
So what happened?
vertical transformation to up.
It went up 2 and it went over 3. Because right now it has a vertical asymptote at 0, but the one we just saw has a vertical asymptote at a 1 and a 2 and a 3, and it's over here somewhere. Okay, so hold on. If this is the actual graph, let me go ahead and make it blue just to make it all official. This is the actual graph. Then how would we describe these transformations? What did we do first? Okay, we did a vertical reflection across the x-axis, so I'll say a vertical flip. What else did we do? Then we did a horizontal flip, and then what did we do? Then we went up 2, and then we went. If we went in that order, we get the graph. There might have been another way of doing it though, Jessie.
Okay, so for horizontal, don't you usually do the opposite?
Opposite. Help me out.
Instead of going like.
Oh, yeah. Well, that was the first. Actually, I guess I didn't do vertical first. Didn't I do horizontal first, then vertical? But wouldn't have really made a huge difference.
What I mean for the shifts, like wouldn't you have had to shift it before? Because it's like. Because if you're distributing the negative to the 3,
See this. You're bringing up the question that we need to ask ourselves. Horizontal, vertical, flips. Okay. The order that we technically did it is we did a horizontal flip first, then we did a vertical flip next, then we did a shift up, and then we did a left 3. Which you can kind of see right here in that we have an up 2, we have a left 3 the way it's written. But Jessie's like, but wait a minute, what if you distribute the negative, then all of a sudden you have a negative 3, and that means you should be moving right 3. What do we have to be careful of with transformations? The order that we go in. The order that we go in. We could have distributed this negative x. We could have distributed that negative x. But when we distributed that negative x, what we would have had to do, when we distributed it, we wouldn't have done the outside first, we would have done the inside first. So if we did have a negative x minus 3, we wouldn't have flipped first. We would have shifted to the right 3, and then we would have flipped, and then we would have ended up in the exact same spot. So order is important with transformations as to which order you go in. If you have a negative factored out, then you just do that transformation first, and then you come in. If you have the negative distributed in, you do the shift first, and then you do the reflection. So we just have to be careful as to the order that we go. Brandon.
So, how do we know, like, for sure order?
For sure order as to which order is important. There is a trick. There is a trick. With logarithms, in the sense of, with logarithms, you can find the domain, and you can find where the vertical asymptote is without even having to think about transformations. So my hint with logarithms would be, basically, it's important to know the domain problem, because if we could figure out the vertical asymptote is at negative 3, we wouldn't even have a question of exactly where it is. But besides that, the general rule to transformations, let me try to think of how this goes, is when the transformation is factored out, when the negative, I should say, that's the one that gets tricky, when the negative is factored out, do the flip first and then any shifts. I generally say do the flip first anyway, just because that's usually what you want to do to get the shape of the graph, and then you think about
And
translating
it's
it.
mathematical because you do the multiplication first, then you do the addition and subtractions. So you do the reflections that you're multiplying by -1, then you add.
Like with PEMDAS. So you can follow PEMDAS in the sense that you think of the multiplying, then you think of the addition subtraction. You think of the multiplying, then you think of the addition and the subtraction. What you have to be careful of is, and that's when the negative is factored out, what you have to be careful of is if it's brought in, you're not looking at the whole argument being negative, you're looking at just the x. So maybe a better way of doing it is that you just want to factor out the negative and then think about the flip and then the shift. But up to you. I mean, you can think about parentheses. If you have parentheses, then you do the flip first. If there are parentheses, do the flip first. That might be an easy way of remembering it. And then if there aren't parentheses, then you just go ahead and do what you would normally do, which is the shift and then the flip. Okay, anyway, that was just a quick little exploration because with logarithms and with other complicated functions, it gets a little bit messy as to what to do first. And so I thought that would be helpful for us to look at. But let's go ahead and talk about some easier ones real quick. Easier-ish. Hold on. So let's see if we can figure this one out. My parent function is a log base 2. My parent function is a log base 2. What do I know about log base 2? Well, he's a log that hasn't been transformed at all. So where's his vertical asymptote? X equals 0. Where's his x-intercept? If you need to, you can think of when is, right? X-intercept, when is the y equal to 0? If you need to, you can think of 2 to the 0 equals x. Anything to the 0 power is what?
1.
Here, anything to the 0 power is 1. So you're going to have an intercept at 0, 1. No, I flipped it, didn't I? That was for exponential 1, 0. When x is 1, y is 0. But that was just how you could solve if you forget. But so far, this is according to what we put down for our logarithmic graph, right? Vertical asymptote is 0, point at 1, 0. This could get a little bit rough. Could I get one more point? It's going to be another special point. Not just 2 to the 0 power is 1, but 2 to the, I guess the 4, but that would be like 16. That's kind of yucky.
No, but I meant 2 squared, so 4.
Okay, maybe 2 squared. I was just thinking 2 to the 1 is 2. Can we do that? 2 to the 1, when y is 1, x is equal to 2. That might help us just have another point. So when y is 0, x is 1. When y is 1, x is 2. And if you need to visualize that as to why that's true, just think about exponential form. 2 to the 1 is equal to x. Remember, the y is just the power. So 2 to the 1 is x. Oh, okay. X is equal to 2. Now we have 2 points and we have a vertical asymptote. I think we have enough to kind of move around now. So when we go to G, all right. All we have are shifts. Whew, no reflections, no flipping. That'll make things confusing. So for G, talk it out. What's going on? I have a positive 2 on the outside that's being added. So it's going to go up 2. And then I have a minus 1 on the inside. So when we have just shifting, it's not a big deal. It's like, whatever, do them in whatever order you want. They're all just shifting. They're all just adding, subtracting. So what am I going to shift up to? Well, what do you guys think? Should we shift the vertical asymptote first, or should we shift the points first? Okay. So then if we shift the points up 2, then we're going to go up 2, and we're going to go over 1. There's a new point. And technically, if we were to do it, we would say add to the y 2 and add to the x 1. So that would be 3, 3. I'm adding to the x 1 for going right 1, and adding to the y 2 for going up 2. Same thing with this point. We're going to go up 2, over 1. So we're going to have the point now, 2, 2. Where's my vertical asymptote going to be? Yeah, if I shift him up 2, he stays the same, but if I go over 1, then I have my, and he helps me out because then I can know exactly where my logarithmic graph is supposed to be headed towards. Now, I technically have him touching. He shouldn't quite be touching. He should be a little bit over. But there we go. There's our g of x. The horizontal asymptote kind of helps me to know how far left I should go. And then the points kind of help me to know exactly how high I should go.
One second. How'd you get the point 3, 3?
Ooh, I took my original point, which was 2, 1.
Mm-hmm.
And I added to the x1 and I added to the y2.
Well, that makes sense.
Because if it's going up 2, the y is increased by 2, so 1 plus 2 is 3. And then if the x, if you're moving to the right one, the x is going to add 1.
You did the same with the 2 too. Okay.
Or you can count your tick marks and then figure out your points. H is a little bit trickier. How come? What's he have? Oh, he has a slip. Okay, that's alright. It's not on the inside, so it's not as complicated. So what's gonna happen? What kind of flip is it, first of all?
Across the x.
Across the x-axis, it's gonna be a vertical flip because it's not inside the logarithm. And then what's going on with the 1?
Goes up 1.
It's gonna go up 1. So this isn't inside, so it's not all weird and crazy and backwards what we think.
So
So we can do basically PEMDAS, yeah? So Lucas was last class.
can we just the 2 and 1 it becomes
For this one, are you back on G?
no.
Not 2 and 1. Oh,
for
the
the
point.
vertical flip. Could we just go like 1 and 2? Oh no, it's not
No,
inverse.
It's not inverse. You're thinking this kind of flip. Vertical flip just says instead of going over 2 up 1, what are you gonna do? Over 2 down 1. Right? So instead of going over 2 up 1, it's gonna go over 2 down 1. That's how our vertical flip would go. This point would stay the same because he doesn't flip at all. And the vertical flip just says, oh, flip them, except, oh, but I also have the what? To move it up 1. So moving it up 1, I take this point and I move him. Take this point and move him. And do my vertical asymptote change if I'm just vertical flipping and then moving up? No, it stays the same. I'm losing my points. He went up 1 and he went up 1. Okay, there he is. There we go.
What about the 2 and 1? Oh, you went up 1.
He went up 1, right? So I do the 2 negative 1, but then he had to shift up. So the outside flips work pretty much just like PEMDAS in the sense of you don't have to pull out a negative, even though I suppose you could, but then things would be a little bit weird. You just think PEMDAS, take the multiplying first and then do the addition. And horizontal on the inside, it's backwards of what you think. So if you have parentheses, then you do the flip first and then you do this addition. Okay, blah, 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 blah. Transformations, but we can't stop there. We can't stop there. Kiddos, I don't know if we actually need to write this, do we? I think we already did it, basically, right? So let's just do a quick review, but you don't have to write it down. Reflect across the y equals x line, we already showed that. The x's and y's switch, which means when this one has the point of 0, 1, he's going to have the point of 1, 0. And I could do that 1, comma, no idea. 1, 0. I could take other points and they would all flip as well, and then we end up getting our symmetry and then we're good. Let's keep going. Sting-a-ding. Remember in this section, it wasn't just graphs. We started with algebraic stuff. So let's just do some homework help to finish off today, yeah? Let's just do some homework help to finish off today. So, what are you supposed to do? Solve. Wait, what? Solve. Solve who? Yeah. How do you solve the problem if they give you a y equals and then they give you a specific x to deal with? Plug it in, plug it in. You end up with y is equal to ln of e to the negative 4. It is negative 4, how come? What's true with ln and e? Can I write it a different way? Let's see if this helps. Isn't this the same thing as, and we don't really write this, I'm just showing it to you. Isn't ln log base e?
Yeah.
Of e to the negative 4? Does that make more sense?
Yeah.
So careful, when they give you ln, it's a hidden log base e. So you can use the inverse property of log base of base to the power when the bases match. Yeah, it cancels out. So that might help. Ln and E are inverses of each other, so we can just say -4. The other way of looking at it, did we do the property yesterday where the power comes down? I don't remember. Oh, we didn't do it yet. Okay, it's still coming.
Number 3.
No, but number 3 shows just the canceling out. See? It just says it cancels out equals X, or it cancels out equals X. The other one's coming. Some of you guys were thinking about, like, hey, sometimes logs can be added or subtracted, or like the power comes down. But since we haven't covered it yet, we don't technically need it yet. Wait, what? We should sue. What's true?
It is homework now.
We're done. Now, quick note. Are we done with logarithms?
No.
What was the title of chapter 3?
Logarithms.
Exponential and logarithmic functions.
It's the whole chapter.
It's the whole thing. Now wait, how many sections do we actually have in chapter 3? Have you guys looked? Chapter 1 was 10 sections. Chapter 2 was 7 sections. Chapter 3 is... Oh.
5
Are you
or
just
6.
making up things?
So it's gonna be like a quest, not even a test.
It's going to be a test, but it is only 5 sections. But guys, if we've already done 1 and we've already done 2, do you think this chapter might go kind of quickly?
Yeah.
Oh, so test like on Tuesday?
Now, test isn't on Tuesday, I don't think, per se. Because tomorrow, what's going on?
SAT.
I'm gonna be doing homework in class. Hey, no homework. Chill.
Oh my goodness. All of you in your class, and you're doing the PSAT tomorrow, yeah? Okay. Since you're doing the PSAT tomorrow, Luke and I aren't going to cover a whole section. Even though we could, that'd be fine. Yeah, that's that.
And then you guys listen to us talking and watch the video.
Yeah, we just be hanging out, right? And they can watch it tomorrow. However, does it look like maybe stuff's going to get a little more complicated soon? Yeah.
What's you?
Do you remember some of these crazy things
Oh
like
my
Misty.
expanding
Let's come back-
logarithms and
let's come back to
condensing
matrices.
logarithms like in 240s?
Yeah.
Matrices are later. Expanding and condensing. Ooh, and then simplifying stuff that looks just funnier and funnier. Well, that's
Well.
long. Okay, hold on. Logarithms have these properties, and these properties, we gotta know how to use them. So, anyway, you need to have ready on Thursday, lazy bum. On Thursday, just kidding, you'll work hard tomorrow in the PSAT, right? You have to have ready on Thursday your homework. Try to have answered as many questions as possible, because we're gonna bust into section 3.3 as quickly as possible. We're gonna take only 1 day on it, but there's a lot going on. Some of you might need to start making formula cards for, oh, that change of base formula, he's important. Ah, logarithmic to exponential and back, he's important. These properties, new properties are going to be important. The quotient, power, product. And then the other properties we have are kind of important. A test is coming soon. I just wanted to make sure that you guys knew that and that you stay on top of things this chapter and you don't get behind. Sound good?
Yeah.
I'm going to go ahead and show you guys the homework for 3-2. Some of you might have already written it in your spiral, and some of you haven't, so you can go ahead and be all ready to bust out homework tonight.
How long is it? How many pages did it say?
Yeah.
How many pages did 3, 1, 6,
It's a lot, but what's true about them? Aren't they kind of shorter?
3, 1?
Sorta, kinda, maybe?
2 pages? 3 pages?
There you go, 3-2. If you need to write it down, you haven't written it down yet. There's the homework. Due tomorrow, under class and with the PSAT, do it tonight, or at least tomorrow night. Have it ready on Thursday. So I'm changing it to Thursday.
Lucas' homework is getting done. The farm free.
Are we okay, guys, to hang out for 2 minutes?
Yeah.
We can entertain ourselves?
Yeah, I know.
Let Sean not have to listen to me talk normally takes his test.
There's a lot of
Look
stuff.
at that one. And they're only waiting for a couple of years.
And then walk
Yeah, I
off.
think
It's easy, and then
you actually